All right, so when we find the derivative, remember that gives us the slope at any point on the graph. Another way to say this, and we've talked about this already, is that it tells us the instantaneous rate of change of the function at that particular point. So a lot of you are taking physics, so you've already seen a lot, but there's several applications of the derivatives in science, economics, ecology, all sorts of things. Population growth rates, production rates when we're looking at manufacturing, water flow rates in engineering and city planning, velocity, acceleration. These are all examples of derivatives. One of the common uses is to describe the motion of an object moving in a straight line. With these problems, we'll use a horizontal or a vertical line to represent the motion. So movement to the right would be positive, to the left would be negative, movement up would be positive, movement down would be negative. So if a function gives us the position relative to the origin of an object as a function of time, then we call it a position function. With the position functions, you're often going to see that called S as a function of time, or sometimes it might be X as a function of time, or if we're talking vertical, it might be Y as a function of time. It just kind of depends. I think the S comes from the Latin or Greek word situ, which means location. So you can use the formula distance equals rate times time to find the rate. And what we always need to remember is that rate is equal to distance divided by time. And that's the same as our slope. Okay, the position function, the X is going to be time, the Y is going to be the position, the distance. And so the slope, rise over run, is always going to be the rate, okay? So if we know that that's true, then the velocity function is going to be the derivative of the position function. So this is where being able to come up with that derivative function is really important. If I know my position function, S of t, then I know that S prime of t is going to be equal to my velocity function, V of t, which is really kind of nice. So that's how we find the instantaneous rate of change. So let's go and look at some examples on the next page. So remember that sometimes we talk about instantaneous rate of change, that's our derivative, but we can also talk about the average rate of change, which is the slope between 2 points. So we've talked about this a lot. The derivative gives you the instantaneous rate of the change, which is the slope of the tangent line. The average rate of change gives you the slope of the secant line. So here's an example. If a billiard ball is dropped from a height of 100 feet, its height S at time t is given by this position function. S is measured in feet and t is measured in seconds. Find the average velocity over the following time intervals. When we see average velocity, we know that we're talking about secant line and we're talking about slope. So for each of these, what we will need to do, and I'm just going to look at A, I'll let you look at the rest, is we need to essentially find f of 2 minus, I guess this wouldn't be f, it would be s, our position function, s of 2 minus s of 1 over 2 minus 1. So when you put that in your calculator, you get 36 for s of 2 minus 84 for s of 1 all over 1. And so that we get that the slope, the average rate of change, is negative 48 feet per second, because those are the units that we were given. That's the average rate of change from 1 to 2. What if we make that interval smaller? This is kind of what we did in that Desmos activity. If we make this interval smaller, and you can do the slope formula, I'm sure, for B, we get negative 40 feet per second when you do average rate of change. And for C, we get negative 33.6 feet per second. So once again, what we're just illustrating is that if we're finding the average velocity of the ball dropping over time, if we make the change in time, meaning the width of the interval, as close to zero as possible, then we're finding the instantaneous velocity, which once again is the derivative. And I know it feels like I keep repeating myself over and over again, but this is so important that we make this connection, okay? This is the big idea here. The derivative of a position function is called its velocity function. And then here's a specific use, a specific case of the position function, which is the position function of a free falling object under gravity. So if I stand on top of something and drop, a penny or something like that, that's a free falling object due to gravity. And so some things to remember are that in this class, a lot of the times we're measuring in feet, but you probably know acceleration due to gravity in meters. So here's both of them. In this equation, G represents the acceleration due to gravity. S is your position, T is time. On Earth, gravity is measured at negative 32 feet per second squared, or negative 9.8 meters per second squared. So you do need to know both of those. Although in this class, I know it drives you physics people crazy. In this class, you're most commonly going to see feet, okay? Now, velocity includes direction, which means that it can be either positive or negative, okay? This is the idea of velocity being a vector, okay? Speed is always going to be the absolute value of velocity because it doesn't tell you direction. So speed is always going to be positive. Velocity can be either positive or negative, okay? So let's look at one example here of how we could use this information. Part A is really just an algebra 2 question. Part B is where we're going to use some calculus. So 10 says, at time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. The position of the diver is given by S of t, where S is measured in feet and t is in seconds. First question, when does the diver hit the water? That is going to be when does S of t equal 0? Because the distance above the water would be 0 at the moment that he hits the water. So for part A, that's just solving a quadratic equation. We want to know when is negative 16t squared plus 16t plus 32 equal to 0. This is definitely factorable. You can probably figure this one out. Go ahead and pause and give yourself a minute to practice your factoring. You should get two solutions, t equals, this is supposed to be positive 2, or negative 1. Since we're talking about time, we're not going backwards in time. So 2 seconds is when the diver hits the water, 2 seconds after diving off the board. Now, let's think about the second part here, which involves some calculus. So if we know the position function, the question is, what is the diver's velocity at impact? Well, we know now that impact happens at t equals 2. That's what we figured out in part A. So to find the diver's velocity, we know that S prime of t is equal to v of t. So the derivative of this function is going to be negative 32t plus 16. That's just using our power rules there. We want to evaluate v of 2. So that's negative 32 times 2 plus 16, which equals negative 48. So negative 48 feet per second is the velocity at the moment that the diver hits the water. It makes sense that it's negative because we're going down. We're jumping from up high and going down. One thing I want to point out, notice that I defined the fact that the derivative of S is equal to V of t. That is a requirement on the AP exam. If you start with S of t and then you just start talking about V of t without making that explicit connection, there's the potential that you might not earn a point on any of those free response. So you should always make the connection to the previous function when you're working with derivatives in this way. Okay, so that's some information on how we can use derivatives in the context of rates of change.